Hello everyone. In the last class we have discussed a very important property of fluid known as viscosity, and we have seen that in case of solids we have shear stress directly proportional to shear strain, whereas in case of liquids, or rather in case of fluids, we have the shear stress directly proportional to the rate of shear strain. The rate of shear strain, it is because of the continuous deformation of fluid, and this relationship is mathematically expressed by using a very important law which we call the Newton's law of viscosity. And mathematically the Newton's law of viscosity is expressed as tau directly proportional to d beta upon dt, which is equivalent to du upon dy. Here d beta upon dt is the rate of angular deformation, whereas du upon dy is the velocity gradient. Now from this expression we have got the very important property which we call the coefficient of dynamic viscosity. Let us see, tau can be written as mu du upon dy, and it is this mu which we call the coefficient of dynamic viscosity. This mu can be calculated as the shear stress tau upon the velocity gradient du upon ty. And if we plot a graph between shear stress and shear strain, what we will get? Now, also we have discussed in the last class that the fluids which follows the Newton's law of viscosity are Newtonian fluids. So basically we will talk about Newtonian fluids. So in case of Newtonian fluids, we have the shear stress directly proportional to the rate of shear strain. So if we try to plot it, if we plot the graph between the shear stress tau and the rate of angular deformation or the velocity gradient du upon dy, what we will get? Since it is directly proportional, we will get a linear graph. So for Newtonian fluids, the graph will always be linear. Now it is the slope of this line which represents the viscosity. So we can represent it like this. It is the viscosity mu, which is represented by the slope of this line. Now as the slope increases, so will be the viscosity. So for example, for air we will get a lesser slope. So this line is for air. Let us say that this is for water, and for a more viscous fluids we will have more slope. So let us say that this is crude oil. So from this plot we can conclude that the viscosity is increasing like this as the slope is increasing, or the viscosity of crude oil is greater than that of water and the viscosity of water is greater than that of air. So let us now discuss about the importance or significance of viscosity. Rather, what are the various effects that the viscous forces causes in fluid flows? We know that the viscosity is the fluid property which characterizes the resistance to flow. Now, it leads to forces that are analogous to frictional forces. For example, fluids resist the motion of immersed objects through them. As if we take a steel ball and if we try to sink it in two fluids, say water and honey, it is rather obvious that the steel ball would sink faster in case of water than in honey. And that is because of viscosity, because we know that the viscosity of honey is greater than that of water. So larger the viscosity, larger will be the resistance to flow. Another example we can take that the fluids have a property that it resists being forced to flow through pipes. And because of that reason, we add pumps. Pumps are added to drive the flow through the pipes. So we can now say that larger the viscosity, larger will be the power that will be required to drive the flow. And when fluids flow over a flat plate, it causes a drag force, and that is in case of flat plates, we call that drag force as the shear force. So these were certain examples, some specific examples, which shows how the very property of viscosity affects fluid flow. Now next we will discuss the effect of temperature and pressure variation on viscosity of fluids. First we will see the effect of temperature on viscosity. Effect of temperature on viscosity. Now before discussing this topic, let us discuss the very cause of viscosity in case of liquids and in gases. Are the causes the same? We know that the viscosity of a fluid is the measure of the resistance to flow. Now viscosity is due to the internal frictional forces that develops between different layers of fluids as they are forced to move relative to each other. But in case of liquids, the viscosity primarily originates because of intermolecular forces of attraction between the molecules, or simply we can say that it originates because of cohesive forces. Whereas in gases, the case is different and the viscosity is rather caused by molecular collision, and that molecular collision causes the transfer and exchange of molecular momentum. So this is a very important point which needs to be noted, that in liquids, in case of liquids, the primary cause of viscosity is the intermolecular forces of attraction. So liquids, for liquids we have intermolecular forces of attraction, or simply we will say that it is because of the cohesive forces between the molecules. Whereas in case of gases, it is rather caused by molecular collision. So for gases, we have molecular collision, and during this collision, what happens? There is a transfer and exchange of molecular momentum. Transfer and exchange of molecular momentum. Now, keeping this point in mind, it will now be very easier to understand the effect of temperature on the viscosity. See, if the temperature of a liquid is increased, the viscosity usually decreases. But in case of gases, this is not true. What happens in case of gases? The viscosity is rather increased when the temperature is increased. Now, what is the reason for this? See, for liquids, what happens that at higher temperature there will be a more vigorous random motion between the molecules, and what happens, the because of this rigorous motion, the intermolecular forces of attraction gets reduced. So the intermolecular forces of attraction, if it gets reduced, what will happen? The viscosity will also get decreased. Whereas what happens in case of gases? In case of gases, if the temperature is increased, what will happen? The molecules will gain more energy and they will try to collide, they will collide more rigorously, and if they try to collide more rigorously, there will be a more transfer and exchange of molecular momentum, which is the primary cause of viscosity in gases, and therefore the viscosity of gases increases with increase in temperature. So finally we have that for liquids, if temperature is increased, the viscosity gets decreased, whereas in gases, If temperature is increased, the viscosity is also increased. Now this can be represented graphically or diagrammatically. What we have here, suppose here in the y-axis we take viscosity and this is temperature. So what happens in case of liquids? In case of liquids, the viscosity is getting decreased. So we will plot the graph for liquids like this. This is for liquids. And for gases, we have the graph. This is for gases. So in case of liquids, the viscosity gets decreased, and in case of gases, the viscosity gets increased. Let us try to note down some values. For example, in case of water, if we take the viscosity of water at 0 degrees Celsius, the viscosity is equal to 0.0018 kg per meter second. And again, if you increase the temperature to 20 degrees Celsius, at 20 degrees Celsius, the viscosity value is 0.0010 kg per meter second. Further, if we increase the temperature, suppose say 100 degrees Celsius, it gets further decreased, and it gets decreased to a value very less, 0.00028 kg per meter second. Now taking an example of gas, we take air. For air at 0 degrees Celsius, the viscosity value is around 1.73 into 10 raised to the power minus 5 Pascal second. And at 20 degrees Celsius, it gets increased, and it is around 1.82 into 10 raised to the power minus 5 Pascal second. So at 0 degrees Celsius for air, at 0 degrees Celsius, the viscosity value is 1.73 into 10 to the power minus 5 Pascal second. And at 20 degrees Celsius, it is getting further increased to 1.84 or 1.82 rather, 1.82 into 10 raised to the power minus 5 Pascal second. Now, see, for gases, we have some specific laws which defines the effect of temperature on the viscosity of gases. We have, for gases, we have a very important correlation which we call the Sutherland correlation. And so for liquids, we have the Sutherland correlation, and the viscosity of gases here in the Sutherland correlation, it is expressed as a function of temperature, and it is given as mu is equal to A T to the power 1 by 2 upon 1 plus B T. Now here T is the absolute temperature, and A and B are the constants which are actually determined experimentally at a specific temperature. And for liquids also we have a law which we rather call the power law. And sorry, I've written here liquids, this is for gases. And for liquids we have the power law. The power law which gives the relationship between the viscosity and the increase in temperature, and it is equal to mu is equal to A 10 to the power B upon T minus C. Here also the very terms A, B and C are some constants which are determined experimentally, and T is the absolute temperature. So we need to remember this Sutherland correlation as well as the power law equation. So this was about the effect of temperature on viscosity. Next, let us see what is the effect of the change in pressure on the viscosity of fluids. So as far we have seen that there is a significant effect of change in temperature on the viscosity of both liquids and gases, and let us now see what is the effect of change in pressure on the viscosity. See, in general the viscosity of the fluids depends on both the temperature and pressure. However, the dependence on pressure is rather very weak. So for liquids, the viscosity is practically independent of pressure, and we can say that any small variation with pressure is usually disregarded extremely accepted except at extremely high pressures. For gases also at low to moderate pressure, mu does not changes. So we have a very insignificant effect of pressure on the viscosity of both liquids and gases. Now, in fluid mechanics and heat transfer, we often encounter a ratio between the dynamic viscosity and density, and it is rather expressed as a property which we call as the kinematic viscosity. So let us discuss about kinematic viscosity. So kinematic viscosity is again another property after absolute viscosity. First we have the dynamic viscosity, expressed as mu, and the kinematic viscosity is also expressed by using a Greek letter, and we call it nu. It is nu and this is mu. So this kinematic viscosity is actually defined as the ratio between the dynamic viscosity and the density of the fluid. So mathematically we can express it as mu is equal to nu is equal to mu upon rho. Talking about the units, we have the unit for dynamic viscosity as Newton second per meter square or kg per meter second, and for density we have kg per meter cube. So what we get here? We get the unit for kinematic viscosity. It comes out to be meter square per second. So this is the SI unit. SI unit of kinematic viscosity, it is meter square per second. However, if we talk about the absolute metric system or the CGS system, in the unit, CGS unit will be centimeter square per second, and it is quite very important to remember that this centimeter square per second has been given a very special name in honor of the physicist Stokes. So we call centimeter square per second as Stokes. Can be represented as ST. So we have 1 centimeter, 1 Stoke is equal to 1 centimeter square per second, or in terms of meter square per second we can write it as 10 raised to the power minus 4 meter square per second. So we have two very special units for both dynamic viscosity and for kinematic viscosity. In case of dynamic viscosity, we call it poise, and in case of kinematic viscosity, we call it Stokes. It is quite very important to remember these both terms and the relationship and the conversion, because in numericals actually we will generally encounter the viscosity given in terms of poise or Stokes, or we may be asked to find out the viscosity in terms of poise or Stokes, or even in terms of centipoise or centi-strokes. So we know the relationship between centi is actually 1 upon 100th time of the strokes or 1 upon 100th time of the voice. So this is all for today. We will meet in the next lecture. Till then, have a good day, and I hope you are enjoying my lectures and you are gaining some experience, some knowledge, useful knowledge about fluid mechanics. Thank you.